Well, good evening. My name is Diana Valencia. I'm a planetary astrophysicist at the University of Toronto. Welcome to the 2018 J. Tuzo Wilson Lecture Series. This Wilson Lecture is an annual event hosted by the Physics Department at the University of Toronto in honor of John Tuzo Wilson. Some of you might have known him. He is one of Canada's foremost geophysicists. He made crucial contributions to the discovery of plate tectonics on Earth back in the 1970s, when only there was one Earth-like planet. The field has changed. I wonder what he would have thought. Today, we're on the threshold of an exciting new era with all these space-based telescopes that are giving us thousands of discoveries of exoplanets. How many of them are really Earth-like? How many of them can harbor life? That's something that we've pondered for so many years, perhaps millennia. And our speaker this evening is the perfect person to talk about this topic. Sara Seager is a professor of planetary science and physics at MIT. She is one of the principal investigators on the new TESS satellite, which launched in April and is mapping the nearest stars looking for exoplanets, maybe some of them similar to our own planet. There's a long list of awards I can tell you that she has earned, but I'll keep it short. She's a distinguished alumni of her own physics program at the University of Toronto. She grew up in Toronto. She has been a professor at MIT since 2007. She has won many awards for her research in exoplanets. She was in Time magazine listed as list of 25 most influential in space in 2012, and even has an asteroid named after her. How cool is that? So please join me in welcoming Professor Sara Seager.
Thanks everyone for coming out tonight. I see so many friends here and members of the Royal Astronomical Society of Canada and obviously new people I don't know, so thanks for coming out. I'm starting with this dark sky. Could you just turn the lights down a little tiny bit for a second? I wanted you to see this. How many of you have seen a truly dark sky? And quite a lot of you actually, not from here obviously, but it's incredible really to think about all the stars out there. And I always like to remind us that every star in the sky is a sun. And if our sun has planets, it makes sense that those other stars should have planets also, and they do. And now astronomers have found thousands of planets orbiting other stars. We call them exoplanets. And we're not sure exactly how many have which type, but I actually am personally thinking that every star has planets of some kind. Now our own night sky, if you go to that truly dark sky and you think you can see to 6th magnitude, you can probably see a couple thousand stars. But our own Milky Way galaxy has hundreds of billions of stars. And you can raise the lights up a little now. And our whole universe, we think, has hundreds of billions of galaxies. So how many of you think that there is life out there somewhere? And you're a self-selected audience, clearly. But what I'm going to tell you about today is really, it's not really so much the odds that life is out there, it's the odds that there is life around a nearby star that we can detect someday. And that's the story that I have for you today. Now what I'm going to do is actually answer the questions I get asked most often. And these are questions I get asked from my professor friends like Diana, who introduced me, or from, let's say, the parents of my kids' friends. So other scientists, just other people of all walks of life, journalists. And these are the questions I'll go through. And while I'm going through them, you can think about which of these is the one I get asked most often. And I'll let you know when I get there. So just to orient us, and for people who may not know too much about exoplanets, I'm going to start with this software that comes from NASA. And you can download this later. It's called Eyes on Exoplanets. And I have a little movie clip to show you. It goes fast, so I have to talk a bit fast, but it's a fake image of our galaxy, quickly zooming into a real map of the stars, where the highlighted stars are stars with known planets, and the white ones are stars we don't yet know. This software, you can use it to zoom in to our solar system. And basically, you can go anywhere on the planet Earth. Here it goes to where this was made on the west coast of North America for a spring night sky. And you can see all the stars that are visible to the naked eye. You can superimpose the constellations. And does anyone know what this very special patch of sky that has so many planets is? This is where a space telescope called Kepler stared for 4 years. But honestly, the whole night sky should be filled with stars with planets. Now, if you know your stuff, on the software, you can also type in the name of an exoplanet, if you know one, and it will take you to where that star is located in this map, real map of the stars. This particular one is Kepler 186, and it shows you that there are 5 planets. And if you click on this, it shows you a so-called Goldilocks zone, where the planet as heated by the star may be not too hot, not too cold, but just right for life. Now it gets to the fine print, which says, hypothetical visualization of planet. Because we don't have anything like this, actually. We have no close-ups of exoplanets. We don't even see them directly in most cases. We hardly have any information on them on the whole, other than that they are there. So just instead of being able to show you real pictures, let me just start with some of these NASA travel posters to give you a flavor of what we try to infer that the planets might be like. It's not very scientific, admittedly. This one says Kepler 186f, where the grass is always redder on the other side. And here, Kepler 186f, the one I just showed you, is a red dwarf star. I'll come back to that with more illustration in a moment. But the thought is that maybe if the star is just shining in red light, that the planets may not be green, maybe they'd be a different color like red. Experience the gravity of HG 40307G, a super-Earth. And here it's imagining that we could travel to this other world, and in this higher gravity, parachuting may feel a lot different. Relax on Kepler 16b, where you're the land of two suns, where your shadow always has company. And here it turns out that, there are planets that orbit 2 stars. There's 2 stars, and the planet orbits both of them. And that's what Kepler has found about a dozen systems like that. Well, what I like to say about exoplanets is science fiction's got some things right. So the question to what is an exoplanet? That's a planet that orbits a star other than the sun. Thousands of them are known. And I might have to say because not everyone thinks this, but we expect that nearly every star has a planetary system. So now you all know what an exoplanet is. The question I get asked, now people want to ask the next question, it cuts right to the chase. When and how will we find another Earth? So first we have to look at some numbers. Our own planet Earth is 100 times smaller than our sun. And it is 300,000 times less massive. And it is 10 billion times fainter in reflected light than our sun. So if you were going to, I know there are some students here working on exoplanets, but if you were going to work on exoplanets, which kind of method would you choose to find another Earth? Would you choose one that involves size? Because the planet's only 100 times smaller than the sun. And the problem is that the sun is big and bright and massive and right next to the planet. So you have to somehow deal with the sun before you can find the planet. Or would you do one that has mass? Because the planet is really less massive than the sun, and Earth is 300,000 times less massive. Or would you do reflected light, where the sun is 10 billion times fainter? Everyone's smiling. I'm thinking you may choose the easy way out, or 100. My favorite one, which if I have time I'll come back to at the end of the talk, is the hardest one, the 10 billion number. And these numbers are all hard. I mean, if you think about, let's imagine you're at your house and you're going to build a deck. Like, how many decimal places do you measure that deck to? Like, are you going to go measure the width of it to 10 decimal places? Like, no, you're not going to do that. But this is what it means to find a planet in reflected light. We'd have to have a way to block out the starlight to 10 decimal places. Well, it's true now that most planets are found using the size. And there's a method called transiting planets. I know that like half of you know what this is, but I'm going to explain it for the other half. So what you're seeing in this little cartoon is you're seeing a fake image of a fake star. And can you see the little planet going in front of the star? It's actually true that some planets are oriented just so, like they're aligned just perfectly, so the planet goes in front of the star as seen from Earth. We call these transiting planets. It's quite rare, actually, depending on how far the planet is from the star. In this case, what astronomers see, we don't see this. We can't resolve any star like this. We see this little light curve here. So the brightness of the star is measured as a function of time, like taking an image of the same part of the sky, like over and over and over again. And Kepler did this literally for 4 years. And so you're monitoring the star brightness, and all of a sudden, when the planet goes in front of it, the starlight drops by a tiny amount. And then when the planet finishes transiting, the light curve goes back to normal. Okay, so this is the main way that planets are found today, although there's at least 5 different ways that planets are found. Now, just it's actually, for Earth, it's a tiny drop in brightness because it's the area, not the size. So it's 100 squared, which would be 10,000. So it is a tiny number. But we've still managed to do it. And just so you know that, like in university campuses across the country here, not all of them, but many of them will have a telescope outfitted with the right type of camera that can look at the drop in brightness, not for a small planet, but for a big, massive, hot planet. And they can actually do this like as part of the undergraduate curriculum. In the northern hemisphere, there's almost every night there's a transiting planet, usually a giant planet. And it can now be like a university project to go and measure it and to work out the math and then extract the size of the planet. So to make our life easier, actually, astronomers even go a step further, actually. And what we're doing now, I say we collectively, because I personally am not, well, I kind of am, but not totally working on this, that we go after a really small star. So this image is now showing you a real image of our sun, and it's showing you, relative to scale, a small M-dwarf star. There are actually these really tiny stars out there. Any of you heard of TRAPPIST? TRAPPIST-1, a bunch of you. But look at that. Can you imagine there's stars that are like this tiny? They're like a tenth the size of our sun. And there's everything in between, actually. Now look at this fake planet here. See, it covers way more area of the small star than it does of the larger star. And so looking for that drop in brightness caused by the planet blocking out starlight, it's actually way easier to find them around these small stars. We kind of call this the race to the bottom, to after the smallest ones out there. But the community kind of goes back and forth. It's like not always the best thing, right, to take the easy way out, because sometimes it's just not the best thing to do. But I wrote some numbers here for the people who like to see the hard numbers, that it's much more favorable. The planet to star area ratio for an Earth around a sun, transiting a sun, is 1 part in 10,000. For the Earth transiting a small star, it's 1 in 100, which is way more favorable. The probability to transit depends on how far the planet is from the star. And for a planet that's in the right distance to be not too hot, not too cold, but just right for life, for our Earth sun, our Earth is quite far from the sun, and the probability for an Earth-like planet to show transits around a sun-like star is only 1 in 200. But for these small ones, it's much better, 1 in 30 or even 1 in 10. So I'm going to tell you about one of the most famous planetary systems called TRAPPIST-1. And I've got a few things to tell you about this one. So you may wish to look at these images showing, look at this. This would be the size of our sun in this corner. Huge, right? This is the size of TRAPPIST-1. And this would be Jupiter. So some stars are so small, they're almost the size of Jupiter. Now, a really interesting thing happened for the team that went to find this. They did a pilot project to look at the very smallest stars out there. Now, TRAPPIST-1, any smaller and colder, it wouldn't be a star. It would be too small and cold to have fusion in the center. It wouldn't be able to shine. And they only looked at 20 stars in their pilot program. I mean, it's so lucky they found this incredible system with 7 planets. And they're shown here to scale of how big they are, but they're all white because we know nothing about them, only that they're there, and we also know their orbits. And I just wanted to show some data for the people who are data-oriented, but you don't have to understand these plots to understand the rest of the talk. You can see here, here are all the planets, and the further they are from the star, the slower they move around the star, and the duration of the transit is longer. But what happened was when they found this system with a ground-based telescope in Chile, a 1-meter telescope or so, they only saw 3 planets. And the team got some time on a space telescope called Spitzer that stared at the system for 21 days. Same comment about data again. This is the day of observation. So 1, 2, 3, 4, 5, up to, this is showing you 1 to 23 days. And this is showing you the drop in brightness of the star. And basically the star is doing nothing except when all these things go in front. And each one of these little drops, the graph is now compressed, so you can't see like this transit light curve. But look at that. 7 of them all here. Now, those of you who are looking at this plot, do you see anything unusual? There's a rise in brightness, not a drop. Because when a planet goes in front, it blocks out light and makes the star dim a little bit. Anyone know what this is? Well, it's a flare, and we'll come back to that. Now, I know the graphs are tedious for some people, especially if you're not graphically oriented. So instead of dwelling on those, let me take you on a virtual trip to a planet orbiting a small M-dwarf star. I'm using this artist conception, but let's imagine that we could go to a planet like that. The first thing is, depending on the planet and star, or the sun, may be very big in the sky. Here, there are other planets in the same system, seen in the sky and seen transiting. The artist has used like an artist license to make the sky colored. It turns out that most exoplanets we can observe seem to have clouds or haze of some kind. And it's true, the sky may be a different color. But what's really interesting, actually, is that the planets orbiting M-dwarf stars that are close enough to be heated to the right temperature, they actually have a very special configuration. They're what we call tidally locked. Like our moon shows the same face to Earth at all times. These planets, due to tides, they end up rotating one time for every orbit. They show the same face. That actually means if we could go to that planet, what that means is that one side is always in daytime, and the other side is permanently in nighttime. So where would you go? Would you go to where it's always day? The astronomers here in the front row, they would go to where it's always night. Or you could go to where the sun is always setting. The other thing is, because the planet is so close to the star to be the right temperature for life, that we could, let's say, survive if we ever had a way to get there, by Kepler's third law, the planet is also orbiting the star quite quickly. So a year would only last like 10 days or 20 days or so. So if there are any kids in the audience, that means your year would be 20 days, your birthday would be every 20 days, which might not be so good for your parents. Now, on second thought, going to this planet could be a disaster for us, because the planets have flares, the stars rather have flares. High energy particles may be flooding, occasionally or frequently, being emitted from the star and hitting the planet. For us, that would be bad. What kind of sunscreen would we bring? We may get mutations to cause cancer. And so astronomers aren't sure really if these planets even have atmospheres, if this wind and the high energy particles have completely ablated the atmospheres. We're not sure if all of these high energy particles are harmful for life. Maybe life has to live on the very dark side of the planet. We go back and forth about it. We know they're the easiest ones to find, but we're not really sure. So here's a picture of our sun with a flare. And I wanted to tell you about this really fascinating event that happened in the 1850s called the Carrington Event. Anyone heard of the Carrington Event? The people in the know, yeah. It was an incredible thing that happened where a British astronomer was looking at the sun. In those days, they didn't know that, trying to understand sunspots, and he saw a whitening around the sunspot. And 1.5 days later, our Earth was charged. It turned out, they didn't know at the time, but a small part of our sun had been ejected from the sun, like a tiny little bundle. It also had a magnetic field, and it came hurtling towards Earth. And it interacted with our magnetic field, causing a current. And back then, the telegraph operators could take the batteries out, and their telegraph would still work. Some of them used the telegraph, and their hands burned. People could see northern lights almost down to the equator. And those that saw them around this latitude would have been able to read by them. Imagine that happening today. There was a miniature event in the 1980s, remember, with Quebec and everything. And now that's fine, but in the US, actually, it's a concern, because if we get that again, our power grid in the US, it's not actually set up like it is here to handle that. So why am I telling you this? Well, by the way, and back then, Maxwell's equations weren't articulated. People didn't really understand the connection between flares and sunspots and magnetic fields, so none of this was really well understood. It turns out that the Kepler Space Telescope looked at a field for 80 days that had the TRAPPIST planets in it. And they saw 40 flares. And one of the flares, people estimate, because Kepler's looking at visible wavelengths and you have to extrapolate to understand the total energy, they think one of those flares was as energetic as the Carrington Event. So imagine we're visiting this TRAPPIST planet, and every 80 days or so, you get a ginormous flare event that is like the Carrington Event that I just described to you. It doesn't sound like a great place to go. So we're really not sure about these M-dwarf stars. Honestly, here it says, we like them because they're easy to find, but on the other hand, we're uncertain because the environment may be so horrible, but then we have to look because we're compelled to find out what's out there. So what we're doing is, I'm going to tell you about TESS now. TESS is called Transiting Exoplanet Survey Satellite. I just put some notes there for people who are interested in the details, but basically TESS is going to find more of these planets orbiting red dwarf stars, transiting planets actually. And the goal is to map most of the sky, looking at all of the bright M-dwarf stars and any other stars that fall in the field of view as well. Now TESS, what it is it actually is a spacecraft. It's actually not very big. Look, this is the whole thing. This is the real TESS back last spring with people in the clean room working on it. And here there are 4 essentially glorified telephoto lenses. They're only about 10 centimeters in diameter. Now, right now, they have giant baffles to block out scattered light, stray light from like the moon or the sun or other things. And they have these covers on, which came off before it went into the launch pad. It has these solar panels, which were folded up, the only deployable. And it has this Ka band, this dish for communicating. The launch was spectacular. It actually happened during spring break, which here I know it's March, right? Kids have time in March off, but where I live, it's like they have 1 week in February and 1 week in April, so it fell on the school vacation. So I was able to bring my family down, and tons of people were there, and we had this like totally spectacular launch. It was beautiful. But we had to be 6 miles away, so that's like 10 kilometers, so it was only like that big. Nonetheless, the plume was just so bright. And it's hard to describe the feeling when something, I work on TESS, something you've been working on, it's all there, like up in this tiny top part of this little fairing here. And all this like energy is putting that thing in space, and you just cross your fingers and hope there's no accident. Well, TESS actually, what it's going to do is it's looking for planets around nearby stars. I have this little movie, which you may like. It's a schematic showing you in yellow. It's actually zooming out from our solar system, showing you in yellow predicted stars with planets that TESS might find, showing you that they're relatively close to Earth. It's also showing you, for those who do know what Kepler is, where the Kepler planets are. So the Kepler stars with planets are like thousands of light years away, and the ones with TESS are much closer. So the motivation is to find planets transiting bright stars that we may be able to follow up to get more information on. There's another sort of little joke about TESS. TESS actually, look, it's like here, and it's beside this giant space telescope that it hasn't launched yet, called the James Webb Space Telescope. James Webb is kind of like the next Hubble, bigger, and it works in the infrared, and it's going to a very special location that is very quiet. But TESS is like our finder scope. So if you're an astronomer and you have a really nice telescope, a big one, you'll have a little tiny telescope attached to the bigger one that helps you find the stars that you want to investigate in more detail. So TESS is finding lots and lots of planets that we hope we can follow up and study them in more detail. So here's a Starfield. This is actually a simulated image of what TESS would see, because I want to convey to you how much real estate, how much part of the sky TESS is looking at. This is about 1 square degree. If you like put your hand up to the sky and you block out the light, that's about ½ a degree. So this is like putting your finger up like at arm's length. That's about how much of the sky it is. But one of TESS's detectors is actually 12 square degrees. So the 1 square degree that would be like a big finger in the sky would be this big. That's one detector. But each of these little lenses, each camera, or each little telescope, and there's 4 of them, has 4 detectors. So it's quite a big pot. That's 24 by 24 square degrees. It's so big that Orion would fit in it. And there are actually 4 cameras. So TESS is looking at a large part of the sky. And here's a real data from TESS. This is just actually a small 3/4 of one detector and 1 camera. But I just wanted you to see how beautiful the data is. Believe it or not, it's my job to run the team at MIT, whose job is to find planet candidates. Like, that's an actual job, finding planets. And it is actually more tedious than it sounds, actually. It sounds like, yay, just discovered another world. I mean, can you imagine if there's intelligent civilization not too far from us who have their own version of TESS, or maybe more sophisticated, and they see us one day, and there's just students like in a room and staff checking it off. Well, this could be a planet, it could be a binary. Let's just toss it. So we find planet candidates basically each of these sectors, where each of these was where Orion might fit in. And the cameras are put on the telescope, on the spacecraft, so that they look at this giant strip of the sky we call one sector. And TESS is looking at the southern hemisphere first. It looks for each of these sectors for 1 month. If you're interested in space, I encourage you to look up the orbit. It's got a really exciting orbit. But essentially, every month we get new data. And our computer searches for, our computer does a lot of the work, looking at literally measuring the brightnesses of all of these stars over the course of 1 month. And the computer flags any events that are that little tiny drop in brightness. And it also assigns a bunch of diagnostic metrics with it. And we have 2 or 3 things in parallel. One is, believe it or not, we have human vetters. We train people, like our students and postdocs and staff, to literally flip through all of them on software and clicking boxes. I know it sounds sort of old-fashioned. Planet candidate, it could be a binary star, it could be instrumental noise, like junk, or it could be a variety of things. And once that happens, in parallel, we're also trying to do that automatically with something we call RoboVetter, which was used for Kepler, which was like an automatic way to do what the human is doing. And in the third category, we try like machine learning and artificial intelligence, which could just be a fancy way for classifying objects in large data very quickly. So we do all those things, actually, and it's quite amazing how far this field has come. Now, once you have a planet candidate, a little light curve, it gets farmed out to literally observers all over the world who have to do a lot of due diligence to make sure that it may be a planet candidate and not a binary star or something else. And there's a lot of details behind there that I won't get into. I just want you to know that there are lots of people. In fact, we had to do a somewhat complicated password-protected system because we're not allowed to make data public because we have to have quality control because it's NASA. And I wanted you to know how many people signed up. Like if you're an astronomer, if you're an amateur astronomer or a professional astronomer, you could sign up to get the data, these planet candidates, to help follow up. And how many people signed up for this website? I want to say it was like nearly 900 people. So can you believe there's like 900, mostly professionals, some amateur astronomers like interested in this who have some means of following up these planet candidates to see if there's planets. It's actually a huge number. I don't know if it sounds big to you, but I don't know, there's maybe like 5,000 professional astronomers in the world. And so some very large fraction of them are really interested. So how will we find another Earth? We're doing this fast track. We're looking for transits around these small stars for Earth cousins. I call them Earth cousins instead of Earth twins. And we'll use transits, the most favorable planet finding technique. Okay, admittedly, that little squiggly line doesn't necessarily look like an Earth, but I'll get back to that in a moment. So in case you didn't think about it, the question I get asked most often is, can we go there? This is literally the question that people ask me over and over again. Anyone know the answer? No, we can't. Well, let's talk about distances. So imagine this is the size of our sun. How big do you think Earth is compared to this? There's a little hint on here. By the way, that is actually a real sunspot. Yeah, it's about the size of our Earth. So the question is, if this is all to scale, how far away do you think the Earth is from the sun at this size? If that's the size of Earth and the sun is that size, you can put up your hand if you think it's where you are. Okay, someone at the back of the room is putting up their hand. Anyone in the front want to, or? No, you don't have to. Okay, well, it turns out that our Earth is about 100 sun diameters away from the sun. So imagine if that's that, we'd have to stack 100 of them. So I think it goes beyond the back of the room here. I mean, most of space is just empty. Now, if this is our sun at this scale, where do you think our nearest star is? You can probably guess. Think of like the furthest away you can get here. We'll say Vancouver, okay? Yeah, so it's far, really far. Everything is just so far away that our fastest spacecraft now, like the Voyager 1 spacecraft, that's not our fastest one, but it's among the fastest, is traveling at 20 kilometers a second. Not an hour, but that's 20 kilometers a second. And it would take like 70,000 years to get to the nearest star, even if it was heading in that direction. So that's tough. Can we go there? Not for now. But what's really interesting, before you start laughing about this, is that in exoplanets, the line between what is mainstream science and what is completely crazy is constantly shifting. And so it turns out that right now, there's a project going on called Starshot, and this is funded by a Russian billionaire. He's funding it to $100 million. That's like serious. That's enough to like move the line a little bit. And this project isn't to send humans, so you unfortunately won't have a chance to go there. But the idea is to send these little, lots and thousands of like little tiny satellites. They're calling them star chips, not starship, but star chip. And these star chips, they're showing you how big part of one is. They would actually go to space and be deployed, and they would deploy a sail that's about 1 meter in diameter, a solar sail essentially, or a sail. And what they'd have to do is have I know it's a little crazy, but they have to have a bank of lasers on the ground. And these lasers would have a huge amount of power, and they would funnel towards these little sails. And they would accelerate them to about a 20th the speed of light, taking 20 years to get to the nearest star. And they wouldn't stop. They have no way to stop. So they'll zoom by, snap a few photos, and send those images back, at least for the satellites that survive, or the space ships that survive. Now, they're really honest. If you go to their website, they will list all of the technical challenges. They have 19 of them, actually. And so money's going down to buy down these risks. So my favorite technical challenge, which I literally thought it was the hardest one, would be to get these telescopes. They're literally telescopes, but instead of focusing the light to them, they're focusing the lasers to go out. And they have to have adaptive optics to correct for our atmosphere, which would mess up these beams. And they need like 100 gigawatts of power. That is like a billion 100-watt light bulbs. Now, who would be crazy enough to give them land? You'd need a square kilometer to put all these things there. You couldn't have anything flying overhead with all that. Those lasers would just destroy it. I mean, really, I thought, like, which country would have that? Like, it's not Canada, so don't worry. So I was chatting to someone who's closer to the project than I am, and he said, actually, they're already in talks with people in New Zealand. So the fact that they, like, it sounds like totally crazy, but honestly, if someone comes back here, maybe not 20 years, maybe it's more like 50 years, you might not even be laughing about this. So this line is constantly shifting. So by the way, let's say for a moment, imagine for a moment we did have a way to travel. And we had a way to travel at, let's say now, a tenth the speed of light. So it would take 40 years to get to our nearest star. Would anyone go? Let's say we had a way to do it. Would you go? There's always people who will go. I mean, it's the human nature and the drive to explore. That's why we're looking for planets and why I hope that someday we'll figure it out. Well, I forgot to mention it's a one-way trip. Would you still go? Yeah, people will still go, I mean, honestly. And if you're age 20 right now, like you're in university, you're a college student, then when you get there, you would be 40 years, you'd be 60. And like 60 is like the new 40, so plenty of time. So by the way, when people ask me, can we go there? And I go through this thing and I say we can't go because we can't travel fast and stars are so far away. Then people say, well, why are we doing this? Why are we looking? So yeah, it's because we can study things remotely. Now, just for the Star Trek fans out there, science fiction, it sometimes got things wrong, unfortunately. They said we had to travel there, like the Star Trek, the Enterprise would have to travel great distances at incredible speeds to get an orbit close to alien worlds so that Spock could analyze if the atmosphere was habitable and if there were life forms on the planet. So I hate to, so it turns out if you made a movie or a TV series about what astronomers do, like Diana in the front and myself and others, it would be incredibly boring. Like honestly, we spend so much time just dealing with data and all our other jobs to help run the university. It wouldn't be a very good movie. And so, in fact, we don't have to go there at all. We use our telescopes, like the Hubble Space Telescope and like large ground-based telescopes. And in the future, we'll use even more bigger, better telescopes. 30-meter telescope, Canada has a big part in this. That's going to go in Hawaii. We use our telescopes to do remote sensing to study planets from far away. And I do want to explain this to you a little bit because I want you to know how it's a little kind of convoluted if you're not used to this topic, but it's how we hope to find these planets and study them and identify a planet that might be like Earth. Well, I'm starting with the rainbow. And what is really interesting about this rainbow is if you could look at it in a lot of detail, you would be able to see that certain pieces of the rainbow were missing, literally missing. And here I have a picture of the rainbow, not from raindrops, but it's by an instrument called a spectrograph inside of a telescope. In this case, it's our sun. So if you could literally see the rainbow in this much detail, here's what you'd see. See all these black lines? Some are fat, some are thin, broad, narrow. These are due to atoms in our sun's atmosphere, and some of them may be due to molecules in Earth's atmosphere. and they're absorbing radiation. They're literally taking bites out of the light. And each atom or molecule has a special fingerprint, a special color or wavelength where the molecules do their absorbing. And people can piece together, using quantum mechanics and computer codes, which molecules and atoms go with which lines. And so from this, you'd need a lot of training, but you could literally tell what was in the sun and how much of what. And this is atmospheric science. This is how we study many, many things in our galaxy and in our universe. So spectra are required to identify a planet as Earth-like. So for example, our planet Earth and our so-called sister planet Venus, they're about the same size. They're about the same mass. And to any planet-finding technique we have today, they will look the same. Meanwhile, our Earth is like an oasis. We have water and we have life. And Venus is so hot, the surface is hot enough to melt lead. So it turns out that transiting planets, again, are amazing for us. We actually, now I'm showing you the same one I showed you before, and I'm showing you an artist's conception, showing you this glowing atmosphere, exaggerated and faked. But the point is that the sunlight can shine through the atmosphere. And the features in the atmosphere the molecules in the atmosphere can absorb light, just like I showed you that rainbow, but it's more complicated and more difficult. It absorbs light, actually. So we can take a spectrum of the star by itself, and we can take a spectrum of the star when the planet is in front of it and subtract them, and we can very painstakingly try to figure out what's in the atmosphere. And there's students here and everywhere, and researchers who do it. It's totally un-Canadian of me to say this, but I actually invented this technique. And now it's the standard way that we look at these atmospheres. And by the way, I have been working exoplanets for like quite a long time, let's say 25 years. And you may not know this actually, so I'll just mention this, but when exoplanets were first discovered, people didn't even believe that they were real. Because think about this transit, right? All the methods that we have to really study them in detail, they're indirect. We just see the star, we don't really see, the planet. And people thought it couldn't be planets because all the planets we find are really unusual. Many of them are like hot, like a Jupiter where an Earth should be, or an Earth, size of Earth mass planet, that is in such a short period orbit. Some of them, their year or their time they take to go around the sun is like less than 1 day. Planets are so hot, they're so cold. We have all sorts of crazy systems out there. People wouldn't believe it. And they never thought we'd be able to study their atmospheres. People just thought that it was just so hard to find them that it would never happen. And today we do. We have like dozens of planets studied with their atmospheres. So I do have to go into a bit more detail, and you don't have to understand these few slides to understand the rest of my talk, but I wanted to give some of you something more substantial. This is showing you some molecules and the sort of Wikipedia version of spectra. So instead of like the dark bands, there's actually a shape to these bands. Some are broad, some are narrow. And you see here they're showing you methane and nitrous oxide and oxygen and ozone, carbon dioxide, water. And it's showing you from 0 to 1. So this is the bigger this colored part is, shows you how much is absorbing and where it's absorbing in color or in wavelength. So you're supposed to see from this plot that on the whole, most of these molecules, at least the limited numbers of ones shown here, actually have specific features, right? Like every one is supposed to have somewhat of a unique wavelength and pattern. So I wanted to draw your attention to this little feature right here. It's between 1 and 1.6 microns. This is water, actually, water vapor. And it just so happens the Hubble Space Telescope, not built for exoplanets, an instrument not built for exoplanets, has a detector that is actually very good at these wavelengths. It works right here. It's such a tiny part. We'd love to get this whole picture, but we only get that. And there is a planet that has that same feature. And that's what this little bump is here. It's actually that same water vapor feature found through looking at the planet as it's in front of the star and subtracting that from when it's not in front of the star. Now, what you're seeing here is wavelength in microns. So you can ignore this part of the plot. This is 1 to 1.6 microns. And here, this is a little complicated, but for those who want to hear this or want to absorb, what you have to imagine about this atmosphere is that where the atmosphere is not absorbing, the planet is a certain size. And where the atmosphere is absorbing, the planet looks a tiny bit bigger. It's like having a fog that you can't see through. Something that's absorbing in the atmosphere blocks the light. And this is the way that we find exoplanet atmospheres and study them. And this is showing you like size, if you will. And it's showing you that it looks a little tiny bit bigger where there's this water vapor feature. And the black points are real data, and the lines are models. That was really complicated, and I know that it wasn't intended like to reach everybody. But believe it or not, that in its kind of convoluted way is the way that we're going to study exoplanet atmospheres. And in small planets, we're going to look for water vapor, and we're going to look for other molecules. And there are like dozens of planets right now, but they're all like hot giant planets being studied right now. So for exoplanets, so right now we have like dozens of atmospheres observed, but they're all big planets or hot planets, or there's something kind of crazy about them. Our telescopes aren't really good enough to be able to look at small rocky planets, even around those small stars yet. We're all waiting for the James Webb Space Telescope. And here in Canada, in Montreal, there's a professor who is built an instrument that's going on it. And the whole community, like literally those hundreds and hundreds of people are waiting this. But for an exoplanet, we honestly don't know what gases we should look for totally. But the idea is first to look for water vapor, because on a small rocky planet, there will only be water vapor if there are liquid oceans. And all life as we know it needs liquid water, so we feel like it's a good place to start to look for liquid water. We have so many gases. That's what this image is supposed to convey. On our planet, oxygen is our the best gas to signify life. And again, if there are some intelligent aliens not too far from here with the kind of telescopes we're hoping to build, they would look at our Earth and they would see oxygen and they would know something is amiss, because oxygen is a highly reactive gas. It really shouldn't be able to exist at all unless it's continually produced. And on our planet, our oxygen is created by plants and photosynthetic bacteria, and it fills our atmosphere to 20% by volume. So our whole atmosphere has been completely re-engineered by life. And so that's the first thing we want to look for is oxygen on another small rocky exoplanet. However, our own planet didn't have oxygen for like half of its life, actually. And so we try to think of all the possible gases that might be out there. And that's one of my main things that I work on now, in addition to TESS and other things. It's this kind of, I went, just for my professional colleagues here, I went off on like this giant tangent in like data fusion and thinking about all molecules that could be in gas form at room temperature and pressure. And in parallel, all molecules that are of any kind that are made by life. I have this like giant kind of chemoinformatics project, and what this picture is showing you is illustrating like a sea of molecules. Imagine that there are so many gas molecules that are possible. We don't know if any or which might be produced by life. But this is showing you 3 different streams, like a subset of choice molecules make it through a filter, or like the concept that life might make some of these molecules. And it's showing you 3 streams, some of them that are never produced by life, some that are produced by life, and some that might be, hoping that we'll have the right menu of options so that when we get spectra, we'll be able to try to decipher whether there might be life on that planet or not. Okay, so transits are only the first part of a long story. They're limited to these systems that have a fortuitous alignment where the planet and orbit just happens to be going in front of the star as seen from Earth. And these transiting planet atmospheres, they're limited to Earth cousins orbiting small stars and not Earth twins. I wanted to explain this to you, like how I feel about the M-dwarf stars versus the sun-like stars. Imagine for a moment that you've gone on 23andMe, and I know a lot of you probably have, and you find you have a relative there. Maybe it's a cousin who is like a different generation from a different country. They don't speak the same language. This actually happened to me, by the way. I went on 23andMe, and it said like I had a first female cousin. I do have 2 first female cousins, and it's not them. So I was like, wow, this is so mysterious. And I wrote to the person, because you can contact them, but this was anonymous. I was like, hi, I'm Sarah. Who are you? I'd love to know. And I just wrote a couple of times for nothing, so I sort of gave up for a while. And then some other people went on, because eventually more and more people go on, and I was able to trace back on my family tree who it was. It wasn't actually my first cousin. It was I think it was like my mother's cousin. So it was my second cousin once removed. And it wasn't. It was like this lady, she's in her 80s, or maybe she's 80 or 90. She's like on her 4th husband. She's from California, which may as well be another country. And so it wasn't really anyone I might meet or even know. I didn't feel like it was anyone that I would connect with, really. But it's still relative. So now imagine you go on 23andMe, and I'm not sure if this has happened. I don't think it'll happen to you, so just FYI. And it's not a cousin, but you say, wow, you actually have an identical twin. You didn't know about this person. That's like phenomenal. And that's how I feel about the Earth twin. It's like so different from the cousin, the weird planet around the M dwarf star that's just like got these flares, and like we don't know what the atmosphere is, and it has a permanent day side. We don't really know. And so it's my goal, and shared with many people working on exoplanets, to try to study sun-like stars and to try to find planets that we might be able to identify like Earth. And we won't get all of that done like in my generation. So if you're like my age or older, we will find signs or hints. But it's really for the younger people here to really push that all the way through. So I will tell you for like the last part of my talk about how we're going to do that. We are going to try to block out the starlight so we can see planets like Earth directly. And we'll get their spectra and the rainbow with the bites taken out of it. And we'll try to do that. And the goal is to, my goal, and again, a lot of other people's, is to put literally this giant screen in space. And this giant screen has to be a very special shape. So if we were to put a giant circular screen in space, and I'm talking about a screen that's like tens of meters in diameter, and we block out a star, the star actually doesn't get totally blocked out because we have diffraction. The starlight diffracts around the edges of the screen, giving you this pattern. It's called an airy ring pattern. This is like if you were to drop a pebble in a pond. You would see ripples because of the wave interaction. And these ripples in light, like that first ripple, is 100,000 times brighter than an Earth twin would be around a sun-like star. So we can't do circles, actually. It's not going to work. Instead, people worked out mathematically, and there's a whole family of solutions, that you can have a very special shape like this. And the big screen is called starshade. And the starshade, if you were to block out the starlight, the light bends around the edges in such a way to cancel out and leave you, if the star shade is made properly, a very, very, very dark image where you could see planets. This would be like dropping a pebble in a pond, and instead of ripples, the pond is perfectly smooth. And all the ripples are pushed to the outer edges where they're going crazy. And this idea for starshade has been around for like decades, actually. It was first conceived in the 1960s. By Lyman Spitzer along with the Hubble Space Telescope. But it was revisited every decade, but it's only now that we can try to take this idea seriously. So starshade could launch together with the telescope, and its petals would unfurl from a stowed position. And in this one, the central truss, the petals would snap into place. This whole starshade has to be tens of meters in diameter, and it would have to formation fly tens of thousands of kilometers from the telescope. And if it works, it will block out the starlight, and we may see planets directly. And now you know why I told you about Starshot first, which was even more crazy. And I was trying to explain how that line between mainstream and crazy is constantly shifting. Starshade now, it's not a funded project, but it is like a technology project, so it gets money from NASA to get developed. Here's myself and a couple of team members with one of the petals. And look, it's got this very special shape. Look how sharp that tip is. It is really sharp. And it's made in this very special shape because the light has to cancel itself out nearly perfectly to have any chance of finding this telescope. And here's a picture from the NASA Jet Propulsion Lab, which is in California. This is staged, actually it's staged, but it's supposed to show you different things going on for starshade development. Here's a picture of, it's like I want to say it's a half or maybe quarter scale model, showing you how the petal how the inner part would fold up. They actually have a name for this. They call it membrane management, how it folds up and deploys. And there's older pieces of the petals, and this is showing you a version stowed, and here's a smaller one again, and everything. So starshade is a project of the future. And in exoplanets, we're always working on many things at once. Some things that today, like TESS, other things for the future, like starshade. So now I'm going to summarize. What is an exoplanet? A planet that orbits a star other than the sun. When and how will we find another Earth? I want you to walk away with that. Transits. The planet goes in front of the star. And the way that light can shine through the atmosphere, and we can try to see what's in the atmosphere. That's how we're going to do it. But for now, all that we can do is study the small planets transiting those small red dwarf stars. Can we go there? Not for now. If we can't go there, look, I spent a while telling you about remote sensing, how we can study atmospheres from afar. And I'll just finish with this little animation, zooming out from our Earth out to our galaxy. And there really, are so many stars out there, and there've got to be literally billions and billions of planets. We're just hoping that one of them, orbiting a star near to us, has another Earth and has some signs of life, so we'll be able to find it and understand our place in the cosmos. Thank you so much. Okay, do you want me to?
Thank you, Sarah. So the floor is now open for questions. There are 2 mics for people to use. If you can put up your hand, and we'll get to you. Yeah, so you can take.
No, thank you. Thanks for the amazing talk. In regards to star shade, it looks like it has to be pretty much exactly in front of our telescope to do that fancy light diffraction technique. How are you going to move the star shade, especially if it has to be far away from our telescope and therefore Earth, in front of each star we want to look at? And how would that be practical if we want to look at all these different planets, all these different stars, to keep moving that shade from star to star to star when it's this big, delicate umbrella?
Great question. So Starshade has its own spacecraft. The animation doesn't show it. I've actually had that same question for someone who's actually in the audience right now in the past. But Starshade has its own spacecraft, and it has fuel to move around. And you hit it right on that it's really hard because the Starshade would have to align, like it has to move across the sky. And even to the next target, it would take like 1 or 2 weeks. And so it takes a while, and maybe you have enough fuel for, let's say, 30 retargets a year, and maybe you've got 5 years. So you have to choose those retargets, those 150, really carefully in advance and figure out like an optimization problem. If you look at a star, how long do you stay on that star? Like, do you give up? Do you wait a while? Because if you move away, it's going to be really hard to move back. So that's a really big challenge. And it's solved in like, we haven't solved that yet. It's a problem. We don't think we can refuel it, although people might want to. There's a Starshade version called the internal coronagraph. That's kind of like the Starshade, but it's on the inside of the telescope. And that has its own set of challenges. But one idea is you have both the internal one, so the telescope can move around looking for the stars with planets, and the Starshade can move in. It's higher throughput and it's broader band. It can do a much better job for atmospheres, so you may have both. Another one is that you have 2 Starshades. Now we're getting greedy, and so they can move around and do other things. We have to share our telescopes. Like, honestly, Hubble, there's tons of people using Hubble. And so while the Starshade is retargeting, other astronomers can use the telescope for their own thing. So we don't have a solution. We only have these kind of statements of how we know about it and how we're trying to work around it. Honestly, we just hope and believe. It's a bit it's some naive optimism. On the other hand, it's some knowledge of what kind of planets are out there, that there will be planets, and that the systems we look at will have what we're looking for. Oh, yes, over there.
Many years ago, Carl Sagan and Frank Drake were in Toronto to discuss a panel discussion about the Drake equation. Now, this was long before exoplanets had been identified, so there were a number of very vague assumptions which were used in discussing the Drake equation. Is the Drake equation still pertinent, or has it been modified?
Yes, so the Drake equation, by the way, it is vague, like it has some terms in it. It's more for illustration to help you understand the elements that go into it. I actually have my own version of Drake's equation. I asked Drake if he minded, by the way. He's like 80 years old, he doesn't mind. We can repurpose the Drake equation for exoplanets, actually. It has to have a different set of terms. But like the Drake equation, some of those terms we can't measure, like the chance that life is on a planet orbiting another star, the chance that that life gives off a gas that we might detect using the techniques I described. We don't know those. So we can definitely repurpose it, but like the Drake equation, it doesn't have any predictive power. It's just there to help you understand the steps that we're taking to get through it.
Hi, yes, it's a technical question on TESS and the 4 detectors. How does the overlap work, if there is any, or the alignment of the 4 detectors? And if there is an overlap, how do you guys account for that?
Like the fields
with
of
your
view of
spectrum.
each camera and
That's right,
detector don't
yeah.
overlap. Is that what you're asking?
Yeah, how do you manage then the perfect alignment, or do you just have to grab more of an area to avoid something landing like right on the boundary?
We can't do anything about that. There's an alignment and it's fixed, we don't change it. If your favorite set of stars or star lands in the boundary between them, it's just tough luck for you. No, like people are literally waiting to see, because once it launched and it got its orbit, we can now tell you, like if nothing goes wrong with TESS and it goes from sector to sector nicely, you can look up whether your star will be on the boundary or not, but we can't help that. They don't overlap, but we have no control over that. The hope is, because TESS is in a very stable orbit, that even though it's funded for 2 years, that the mission will get extended from NASA with more funding, and that eventually we can cover areas that weren't covered.
So you talked about discovering exoplanets. Have we ever found an exomoon?
Okay, that's debatable right now. I see some people laughing. We like to find moons, actually, but think of how hard it is to find the planet. I gave you the numbers, like 100, 1,000, 10 billion. It's super hard to find moons. And there's 2 ways we think we can find them. One is, if the planet goes in front of the star and causes that little drop, the moon could be following the planet and also cause an even tinier drop in brightness in the star. Believe it or not, if the moon and the planet are orbiting their common center of mass, the actual length of time that the planet appears to be transiting actually could change slightly. And there is, we wanted to find moon. It's the one thing like on our wish list, one of the few things that we haven't got yet. And there was an announcement a few weeks ago that it was very kind of cagey, right? Like there is a moon, there isn't, there may be. And there was a moon, kind of moon found by Kepler, and then Hubble was used to follow up and kind of double check it again. But it's really not clear whether it's real or not, and the authors write the paper very carefully. The difference between what gets in the news versus what is written carefully by the authors could be worlds apart. So if it were real, it's a Jupiter-sized planet and a Neptune-sized moon. It's really big. And it has a bunch of things that are really awkward about it. So we don't really know, but in astronomy here, we can't really get any more data in the short term, or it won't really help the case. So we kind of just publish and then just leave it there for future work to disentangle. But we haven't found any even Earth-sized moons, or maybe we could have reached something a little smaller. And they may be out there, but just too hard for us to find at the moment.
Yeah, what is your strategy for sort of detecting whether spectra from other exoplanets potentially display life form? Like, I really like where you were going with the engineered idea of engineered atmospheres. So have you looked into maybe using quantum computing to fast forward and increase the accuracy of that process? Like maybe taking sort of some sort of quantum signature of the atmosphere of our life and comparing it against other exoplanet spectra.
Okay, well, there's a bunch of different questions in there.
Sure.
So quantum computing, it's like artificial intelligence and stuff. People always want to use it for whatever they have, because it sounds, I'm not saying this in a mean way, but it just kind of sounds cool. Like, quantum computing isn't powerful enough yet. What it could help with, just for a technical answer, is when we generate these spectra, it's very hard to do that, actually. If you want to model like a molecule with many atoms, how it actually absorbs radiation, it takes like years to figure this out. And quantum computing could help us in that direction if we can ever get enough power to do it. But in terms of atmospheres, the way you described it, it is essentially what we're doing. We think of our own atmosphere and what the gases in our atmosphere may look like from afar. And then we try to sort of think of what would another planet look like, and could we ever attribute those gases to life or not? The one thing is that there's a lot of other variables which can affect a gas and whether or not it accumulates in an atmosphere, like the amount of ultraviolet radiation from the star and whether there's oxygen in the atmosphere. So we are doing this kind of comparative approach. But I feel like until we get real data, until we're confronted with real data, we may not really know whether, we may have to revisit the entire thing once we actually get real data.
Hi, my name is Artash, and I was wondering, if the TESS is going to look at each piece of the sky for only around a month, then it would be looking at exoplanetary systems with max maybe an orbital period of 30 days, which would mean that probably this exoplanetary system would be pretty compact. And especially if there are many planets inside the system, this could mean that all these planets could orbit in a harmonic motion. And if we're going to look at it 30 days, we can get maybe, if there's like 6 planets, maybe we'll see a couple dips. And based on these dips, using artificial intelligence, would it be possible to measure actually the size of the other planets.
Okay, well, if we see all 6 planets in the same system, if that's what you're thinking of, they're all compact and we see them all, we'll get all of their sizes based on how much light they're blocking out. So we won't need artificial intelligence for that. To address your question, that he did point out something really important, that TESS only looks at each strip of the sky for a month, and if you have to see 2 transits to get a period, we're limited to planets with like a shorter duration. But you probably couldn't tell from the plot I just flashed by, but TESS cameras do overlap at the poles. So one strip of the sky and then another one. So there's some areas where it will look for much longer than a month. So I'm not sure if that answered your question. If we find these multiple planet systems, not only with TESS, but with follow-up telescopes measuring their mass and size, we'll do a lot more detective work. Okay, let's see, microphone, there's a question here. Okay, question back here first.
Yeah, thank you so much for coming out, first of all. And I was just wondering, so when you're analyzing an exoplanet's atmosphere to try and identify what kind of gases or what its composition is, you're essentially, you talked about how we're looking at how, let's say, oxygen was a key sign of life on Earth, or carbon or nitrogen or other gases might be signs of Earth. What if life on other planets took a completely different evolutionary path from what we're familiar on Earth? How would we identify that? How do we account for that?
That's a great question. It's one I try to think a lot about, and we don't totally know. I mean, there's a very simple kind of picture that we're looking for gases that don't belong. A gas that's produced in such huge quantities, it's like out of equilibrium with all the other gases there. So essentially, we first really would have to see, like, what is there? And then in context, if there's a gas in huge quantities, does it fit or not? And we sort of have to kind of, like a crime scene forensic work, try to work things back and come up with some concrete evidence. It doesn't sound that convincing now that I'm like listening to myself explain it, but essentially that's what we have to do. And there are some gases that life on Earth makes, isoprene, you probably haven't heard of these, dimethyl sulfide, and their spectra, like their spectral signatures are unique enough. And some of them we can't, by thermodynamics or other work, can't imagine that they're just produced by volcanoes or by geophysics. So there are some cases, if they exist, that we would be able to identify. And there are other cases that may just confound us. I mean, we'll just be lucky when we have data and can in the future, if we have that data and have that problem, it'll be a great problem. Microphone. Oh yeah, go ahead. Go there.
Yeah, on the question of how do we get there, so there, you mentioned the solar sail method, and there's a few methods of propulsion systems that we're looking at, like that, or like the ion propulsion method. What would you say is the best candidate that we have right now for interstellar transportation? And what timeline would you, what kind of timeline would you give for that? And if so, which planetary system would you go to?
Okay, so this is not, not my area of expertise, and so my kind of answer is I don't really know. I think it would be great to invest in all of them. Like if I had money and like I won the lottery and I could do it, I would want each one of them to be pursued to see which one might work. I don't think we have a timeline for you. There is a project called the 100-year Starship. And this is a project that was started by the US government, and they put money in like for people to brainstorm and ask that same question, which one or which ones should we pursue? And it's now run by, I can't blank on her name. She's a former astronaut, Mae Jemison, and she now runs this organization called the 100-year Starship. So I encourage you to look that up and see what they're doing. It's kind of complicated. So that goal would be that the original initiative and the name was hoping like in 100 years. Maybe we're not going to go in 100 years, but we'll have advanced enough so we could really start thinking about it. But if I had to guess, I know like that it's going to sound even more crazy. If I really had to guess, if you wanted me to say what do I really think will happen, I will say that hundreds of years from now, it won't be 100. We'll go there, but it won't be us. It'll be like materials. Now they're making like kidney cells in the lab, like not whole kidneys, heart cells in the lab that we will have a way to maybe send our DNA or raw biological material. I don't think we're going to go as humans. I just don't think we can withstand the journey and go there. We'll have to see what happens. But I just think other things are advancing so much that there may be a totally different paradigm that we can't conceive of. Not like the movies, like The Passenger, or these other things where people hibernate and go there. Yeah.
Go ahead. First off, thank you so much for coming out here today. I was wondering, you talked a bit about light sails, small sails propelled by laser propulsion. Do you think that perhaps, even if we cannot detect life, we could bring life to other worlds, put some sort of seed or some sort of microorganism into these sails and send them to other stars and perhaps seed some sort of life that might evolve in a few million years?
I think if we could get to a planet and crash into it, you could definitely do that. There's sort of people actually, I haven't heard this one talked about in detail, but at least for our own solar system, there's something called planetary protection. There's like a real office called that at NASA. And they worry about, I know this is getting a bit far afield now, but is it ethical? Like, is it okay to go and like pollute another planet like that? And you wouldn't even know, right, if it had life on it already. But certainly, you could imagine microbes can like withstand space, and they could go there and seed another world. It could happen. Should we take like a couple of more questions?
Just one more question, and then we'll let Sarah rest.
Okay, there's a paradox called Fermi paradox. How come the sky isn't buzzing with intelligence? And I think it sort of relates to the Drake equation, where it says it's probable to have life, probably intelligent life too. I was wondering, and there are some explanations to it. One is, intelligent life would devise means of, destroying itself, or it's not sufficiently thoughtful, in terms of its environment. Can your method detect any, pollution on other planets, like CO2 pollution, maybe even radioactive isotopes or something like that?
Okay, good question. So you're not asking about the Fermi paradox, which is a good thing. Everyone here, you can each have your own answers to why, if there are intelligent life, they haven't made it here yet. But about this pollution, like, remember how we have like chlorofluorocarbons in our atmosphere? We have like sodium lamps. I know we're trying not to light pollute either, but we have signatures, right? They have a name for it, technosignatures. And people have tried to study this, but that's not something we can do now. The same techniques in the far future, with like much bigger telescopes, may be able to see those. But even though we complain about chlorofluorocarbons and other pollutants in our atmosphere, they're really bad for us, but they're so tiny, like it's seen from afar. Remember, oxygen, 20% by volume in our atmosphere. It's not just like a tiny trace thing that's so hard to find. So to answer your question, it is a goal or a hope for the far future. If we were to find a planet with some signs of life, we could follow it up with future generation telescopes to look for those very kinds of things.
Okay, so join me in thanking Sarah again. There's a reception outside for people to mingle and maybe ask a few last questions. And remember that we have another lecture next year with some exciting new prospects. Okay.